Today on Into the Impossible, we're exploring the fascinating realm of time with none other than the master timekeeper himself, Chad Orzel, renowned for captivating books such as How to Teach Quantum Physics to Your Dog and Breakfast with Einstein. Chad is here to unveil the mesmerizing narrative woven into his latest masterpiece, A Brief History of Timekeeping.
You find that time passes at different rates when people are moving relative to one another.
In the book, he revisits delicate negotiations involved in the Gregorian calendar's reform, the intricate and entirely unique system employed by the Mayans, and how the problem of synchronizing clocks at different locations ultimately required us to abandon the idea of time as an absolute and universal quantity. From sundials to sandglasses and mechanical clocks, this sharp and engaging story isn't just about the science of timekeeping. It's a riveting tale encompassing politics, philosophy, and the very essence of space and time itself.
How do those two things coexist? How does that linear march into the future and this cyclical repetition, how do those play with each other?
So right now, it's about that time. Let's get started.
So, Chad, you've written this wonderful book. It's not new. It's 2 years old now. A Brief History of Timekeeping. I bought you were kind enough to send me the hardcover, the soft cover rather, with beautiful illustration, and we're going to go through it. I listened to it on audiobook as well. I really enjoyed it. As we do on this podcast, one thing is mandatory for authors such as yourself who grace us, and that's to judge the book by its cover. You're never supposed to do it, but you got to do it. And that's to do the following, Chad. So please take us through the title, the subtitle, and the delightful, intricate, modern times looking gears and the artwork. So those three features of the book. Help us judge this book by its cover.
So yeah, the title is A Brief History of Timekeeping, and it's very much what it sounds like. It's a book about the science and technology of tracking time over the last several thousand years. I don't remember the exact wording of the subtitle, but something like the science of keeping time from Stonehenge to atomic clocks, and that sort of gets you the sense of the scale. So it's from kind of Bronze Age, Neolithic kind of monuments all the way up to the current state of the art in atomic clocks, and even a little bit about sort of speculative atomic clocks that will go to even higher level of precision than we can manage now. The gears on the cover, that was the work of the art department at Ben Bella Books, who's the publisher for this. And the minute we saw that those popped. I don't know what that gear train is actually from, but it looks really great, and jumps off the blue cover, and we're like, yes, that's the one tweak. I think they may have rotated the picture slightly just to get the words. The very first pass at it ended up looking like a history brief of timekeeping, and so they turned it a little so it was a little clearer what order the words go in.
It's impossible not to note the direct correlation with the most famous book, the third book that I've written, according to ChatGPT. If you ask it, what books has Brian Keating written? He's written Losing the Nobel Prize, Into the Impossible, and A Brief History of Time. I heard the late, great Stephen Hawking at the Royal Society in 1994 or 5. And he couldn't talk, but he could use a speech synthesizer.
Yeah.
And at the end, he graciously accepted questions. And there was a member of the audience who asked him, Stephen, you've written this book. Almost nobody has read it. Anyone who has read it doesn't understand it. You even claim in the book that every equation reduces the audience by half. Tell me, Stephen, the questioner asked Hawking, why did you write this book? And after 5 minutes of just painstaking silence. We're all just waiting for him to move his eyes across the computer generating his voice. And he said, because I needed to pay for my daughter's college. Chad, you've got 2 kids. You're obviously devoted to your kids and your pets.
Yep.
You write this book for the money to pay for them to go to college.
It's nice to have a little extra money, but I work at a college, so getting them through is going to be not as difficult as it might be in some other circumstances.
Yeah, if you were at UC San Diego, you know what we get here? We don't get free tuition. We get in-state tuition. That's all.
Yeah.
So I
So,
really enjoyed this book, and part of the reason we're talking today, although I want to talk to you for a while, we met in person about 5 years ago now at an APS meeting in Denver, Colorado. It was great to meet you at an event for authors and popularizers, as we're sometimes called. But you're also a hardcore scientist and contribute a lot to cold atoms, and we'll get into some of those techniques. I had Bill Phillips on, who you must know from your time in
oh yeah,
Maryland.
Bill was my thesis advisor.
Yes, I was going to
So
say. I suspected it, given the. I tried to look up some papers that you've written with him, but it was I only had so much time. But Bill was on about a year and a half ago. Just a delight. Love talking to him.
he's
And
fabulous.
we'll get into some topics in the future of timekeeping and where do we go from here and why do we go from here? Why do we need clocks that can do femto attoseconds and whatnot? But one of the reasons that we're talking today is because of a somewhat brusque comment that I made, or maybe you made on Twitter, which is that I was on the Joe Rogan Experience last summer, and I was talking about my hero Galileo, who's around here somewhere in puppet form, and I claimed that he had tried to solve this time problem by inventing this Apple Vision Pro like device with, instead of one camera, had two telescopes attached to it, and the court rejected it, or the people in charge rejected it because you could only see Jupiter 9 months of the year, and you could only see it at night. Where was I wrong? How should I be shamed publicly? What did I say wrong to Dr. Rogan that raised your ire, if anything?
I don't remember exactly the details. The telescope helmet thing that he drew up is wonderfully steampunk looking. It's really quite a device. The idea there is that if you could observe the eclipses of the moons of Jupiter, you can get very accurate measurement of what time it is, and those are very reliably predictable, and you can use that to set a clock. And in fact, people did that a lot in the 1600s. The technology for doing that on shipboard just wasn't there. It's not stable enough, even with the helmet, to be able to really zoom in and see those eclipses and get the timing that you need to do a good measurement of longitude. People were doing that on land, and you could do travel across the ocean, then set up your telescope on land and figure out the longitude very accurately that way. That worked pretty well, but on shipboard it was pretty hopeless. Galileo is also usually credited with inventing the pendulum clock, and he did have the idea to do the pendulum clock, but by the time he had the idea, he was rather elderly and basically blind. So they never got it to work. One of his son and one of his students worked at it for a little while, but never made a working prototype. So it was Christian Huygens, almost 30, 40 years later, who got it to work. Designed the first working pendulum clock and had it made by a clockmaker named Solomon Koster. Who's one of these people who no actual picture of him exists, which is sort of interesting. It's from that time period. Huygens, you can find lots of engravings of Huygens, but Koster is a complete loss.
Yeah, looking at that, although there is some lore, there's so much lore with timekeeping. I mean, it's so important, so integral to everything we do in life and so forth. And you gave it a definition which is in congruence with what Frank Wilczek told me when we talked as well about time. And that's, time is what a clock measures. But that's sort of, tautological. If I said, length is what a ruler measures, or it wouldn't be as satisfying, right? So we somehow will accept that for time, but nothing else. Why is that? Why does time get a free pass?
The phrasing I like to use, I think I lifted from Bill Phillips, actually, is that a clock is a thing that ticks, and it does some regular repeated action that you can count. So, the pendulum on a pendulum clock swinging back and forth, that happens in a very regular way, and you count how many times that happens, and that's the thing you use as the clock. I think the reason that time kind of gets a little bit of a pass there is it's unlike length, unlike space, we only experience it in one direction, right? We move from the past to the future, and we do that in a rather inexorable way. You can't go back in time. And so it has this quality that, well, it only goes in one direction. And so there's sort of more of a simplicity to the experience of time that lets you get away with a very operational definition, like, time is what you measure with a clock, and a clock is the thing that ticks.
Hey there, guess what time it is? Yes, it's time for you to finally subscribe to the show that you've been listening to and enjoying all this time. Well, I found that only about 50% of you are subscribed or following the podcast, video or audio. So wherever you're here, just take a quick second to subscribe, hit the follow button or the plus button, or subscribe on YouTube, wherever you are watching or enjoying this content. It really makes a huge difference and allows me to continue getting great guests like Chad on the podcast. So go ahead, hit that button, and thank you so much for your support. Let's get back to the episode.
The kind of other notion is that the origin of time and conjunction and the measurement of time in astronomy is incredibly intermingled, and I think it would be useful to kind of go over these. And at first glance, you might not think, well, I'm going to talk to an expert about time and then talk to an astronomer, but of course they're intimately related. And I kind of want to get the historical sweep. I hate it when I go on as an author and a podcast host says, explain your book in great detail, so we don't even need to buy the short form, brilliant summary of it. We just need to listen to the podcast. So why is astronomy so irrevocably associated with the measurement of time?
Well, I mean, the most obvious things in the natural world that tick in a really continued way are the motions of objects in the sky, right? So the sun every day. If you're in California, so I'm assuming it's sunny.
Not today. Sorry,
no, it's pretty dreary here too.
Cloudy. But I think it's warmer where you are today in Schenectady.
Yeah. The sun rises in the east and moves across the sky and sets in the west. And that happens every day with amazing regularity. And that's a thing you can count. You can say, okay, well, the sun rose and then it moved across the sky and it set. And now it's risen again, and that's a tick. That's one day. You can make it a little more fine-grained by doing something like, hammer a stick in the ground, and then you look at where the shadow points, and you can say, well, that gives you a little more resolution, finer resolution to subdivide the day. And that works very well. There's also, at night, there's the second most obvious moving thing in the sky is the moon. And that has the really nice property that it also changes shape on a very human kind of time scale, right? Over the course of several days, you see it go from, a tiny little crescent to, the quarter moon and then the full moon. And you see that evolution, and that follows a very regular pattern. Small crescent gets bigger, shrinks down, disappears. Small crescent gets bigger, shrinks down, disappears. Right, that happens over and over, and that gives you another kind of clock. And so it's what is the origin of timekeeping is trying to use those patterns to mark the passage of time, and to sort of predict when is this going to happen again, right? How many days will it be before the moon is full again, or more importantly, like how many days will it be before it's planting season again? Right, before we need to do agrarian things to ensure that we have enough food to carry on as a civilization.
The other thing that kind of resonates throughout here is the application of the measurement of time to navigation, which again, is not immediately obvious to a layperson perhaps. So why don't you speak a little bit about that? It's easy to measure latitude with a telescope and an ability to see at least close to Polaris or other stars even. You can measure it with any star, but in particular. But why is longitude such a difficult proposition to measure?
Yeah, longitude is tricky because the Earth is a sphere and it's rotating, and there isn't the same fixed point. Latitude is easy because you can look at the height of the sun at noon, or you can look at the elevation of the North Star at night, and pretty directly do a little tiny bit of trigonometry, and you get what your latitude is very, very easily. There isn't that kind of fixed point with longitude because that's the direction in which the Earth is rotating. So everything is constantly moving in the longitudinal direction. And that makes it a lot more complicated. The only way to figure out, you can figure out a difference in longitude if you know a difference in time, right? And time is measured by, say, the position of the sun. If the sun is directly overhead for me here on the East Coast, then it's going to be, 3 hours short of directly overhead for you on the West Coast. And that difference tells us the longitude, right? The difference in where we see the sun at the same instant in time tells us our difference in longitude. So you need to be able to know the time at two widely separated locations to be able to determine longitude. If your fastest mode of travel is foot or horseback, it doesn't really matter very much because you're never going to go far enough that you have to worry about that. But if you're going, many thousands of miles on relatively fast moving ships trying to make a globe spanning empire, or later on when you get to things like railroad trains, and then eventually airplanes, right? You can experience these changes in time in a very real way. And then it becomes really important to know when you are, as well as in order to determine where you are.
And of course, the notions of so many of these things are both familiar and terrifyingly, abstract to many people. And throughout the book, you do an excellent job kind of explaining the mindset of the time and what was thought to be the prevailing, best measurements of time. And then all of a sudden comes this guy in 1905 with his paper on relativistic electrodynamics, which we don't normally associate with relativity, and all hell breaks loose. Talk about the challenge of what we just described on a moving framework, on a planet that's moving, around a star that's moving, in a galaxy that's moving. Talk about the relativity of simultaneity and how that was a philosophical upheaval as well as a scientific upheaval.
There's a really good paper. I mentioned it in the book. It's available online, in a translated free form by Henri Poincaré called The Measure of Time. And he makes a really good point that like sort of essentially everything we do when we're talking about measuring time is a matter of convention and sort of choice for convenience, right? We can determine what time it is by looking at the eclipses of the moons of Jupiter. But when we do that, we say, well, we can predict the eclipses because we assume Newton's laws of gravity, and that describes the orbit of those moons, and so we know where that's going to be. And we assume that the speed of light between here and there is finite and very large, and we know what it is. And you put all that stuff together, and then you get something that works as a clock. But you could make very different assumptions about the world. We're just choosing to use those ones because they're convenient to us, right? And so that gets you sort of, time has this sort of, necessarily has this kind of relativity to it, that everybody's experience is a little different, and we obtain some kind of commonality by making a choice of convention. What Einstein pointed out is that, if you look at the behavior of things, you would say the laws of electrodynamics predict that there's one and only one speed of light. And if you, look into that, you can arrange it so that there is in fact one and only one speed of light at the cost of changing our notions of time, and that time has to pass at a different rate if you're moving in order to ensure that there's one and only one speed of light. And this is a thing that is an idea that a number of people sort of encountered, this issue with the speed of light and electrodynamics and how do we explain this and that sort of thing. And Einstein's big point was to point out, sort of going back to what we said at the very beginning, that you can't talk about time unless you talk about how you're measuring the passage of time. You can't talk about time in two widely separated places unless you talk about how you synchronize those clocks at those widely separated places. And when you go through the details of how would you do that, how would you synchronize clocks, how would you get that, you find that time passes at different rates when people are moving relative to one another. And then the whole theory of special relativity unfolds from that.
Can you talk about gravity? And it's not immediately obvious to probably most people that gravity should affect a clock, and yet it does. And can you explain the notion separate from the effects of special relativity on which gravitational fields can affect the passage of time for different observers?
One of my favorite Einstein stories is he described, the happiest thought of his life is a day he was in the patent office and he was thinking about somebody falling from a high place. And, the thing that separates a genius like Einstein from normal people is he was not imagining a specific annoying coworker being pushed out a window. He was thinking, very generally about the physics of somebody falling, and realized that when you're falling, you feel weightless. Like as you're falling, you don't feel a sensation of weight. And that led him to realize that there's this connection between gravity and acceleration. And at the time, he had been trying to extend special relativity, the theory that governs people in motion relative to one another, to include motion that was changing direction, changing speed, accelerating in physics terms. And he realized that there's this connection between gravity and acceleration. So in the same way that thinking about how do you synchronize clocks in separated locations leads you to the notion that people moving at constant speed relative to one another experience time passing at different rates. When you start to factor in the effect of acceleration and say, okay, it can't be possible to tell the difference between accelerating in one direction and having gravity pull in the opposite direction, then that leads inexorably to the conclusion that gravity affects the passage of time. And this is a thing that we can directly measure. You can there's a famous experiment done at MIT in the 50s or 60s where they shot light up a they call it a tower, but it's really a stairwell in the physics building at Harvard, and showed that the frequency of the light reaching a detector at the top was very slightly different than the frequency when it left the source at the bottom. And that difference is exactly accounted for by the effect of gravity on time that Einstein predicted in general relativity.
Yeah, that happiest thought of Einstein actually is a segue, gives me an opportunity to move into education, because when I think about what artificial intelligence may or may not do to us as a species, I think of that quote often, because in what sense could a computer, visualize the visceral sensation of free fall? And furthermore, in what sense could it have a happiest thought? I mean, what is its happiest thought when it's fully charged? I mean, how is it going to relate to these notions of the great Gedanken experiments that Einstein and others practice in? And so you're a master educator. You're known for special attention to the craft of being a professor. You and I can talk shop now that we've passed the 20-minute mark, which is the average view duration for my videos. Shame on you out there. You should watch the whole thing. Actually, if you heard me shame you, you're actually listening. So I love it.
You're doing great. Keep it up. Keep listening.
Stay till the end. By
so
two
either
books.
that or you're playing it on double speed.
That's right. So when we think about being a professor, I thought, part of the book that was written during COVID, as I understand it, your book. And I thought COVID would be the death knell for our profession in some sense. I thought Zoom and paying full tuition, which I assume is similar here, there at Harvard. I just talked to Eric Mazur yesterday. It's $57,218 at Harvard. Look, these are kind of cartel level price tags. And yet nothing really happened differently. We emerged from COVID basically doing the same thing. You and I scrape on a big piece of rock with a little piece of rock. And that's the same as was done in the University of Bologna in the year 1080 when the first Western university started. So are we basically safe from AI overlords? What do you think does the profession look like for master educators such as yourself?
One of the things that COVID revealed, and that having to make that really rapid transition into online education revealed, is that there's really a crucial in-person sort of live element to it that's hard to do without. That you really need the ability to sort of have give and take and conversations and adjust on the fly. That's hard to do online. I did the book came out during a COVID surge, so I did a bunch of speaking events, but they were all remote because it was I think the Omicron or Delta, one of those variants. And all the in-person stuff was canceled, and it's really hard to do talks for an audience when you can't see them directly and you can't interact live in the way you see the little tiny faces on the side of the Zoom window, but you can't really get much from that. And so we did a term of fully remote. We did a term. I taught a course on quantum computing in a hybrid format, and that sort of worked, but it's really hard to have people in the the different places, and have that kind of interactivity and that read the room and adjust things as needed. If I'm going too slow, I can sort of tell and I can speed up. Or if I'm losing the audience, saying like, okay, clearly this isn't landing, I can do this on the fly. And it's a lot harder to do that in the kind of asynchronous video way that you tend to on the internet. When we opened back up in person in the fall of 2020, we started bringing students back on campus in September. It was really something to see how grateful people were to be back in person in school, and the lengths that students were willing to go to, like the restrictions on masking and socialization and all sorts of activities that they were willing to put up with for the sake of being in person, because people really value that contact and that in-person interaction. The tech is almost there, but it's not yet. Maybe some VR kind of thing eventually gets you there. But, as it is, it's still not, there's still something about being in the same room with people that feels really essential to making progress in education.
Friend Galileo and Einstein and Carl Sagan and many others, practiced this craft for so long. But yeah, I do think that there could be some potential opportunities also, because why talk to, me, Brian Keating, and learn, cosmology when you could talk to some avatar of Edwin Hubble. And so I do worry about it. And actually, speaking to Eric yesterday was quite terrifying, because his whole shtick is that we should flip the classroom and have basically the students read the book the night before and catch up and do some problem solving, and then come to class and then debate with their other students. And that actually has a twofold purpose. It actually rewards the students that are highest performing, because they get to teach, and when you teach, you learn, as you and I know, better than just reading and consumption. And it benefits the lower performing students. At Harvard, they have a lot of low performing students.
They're known for that.
At least half of them are below average. I mean, I know that for sure. So, they get the benefit from the students that are highly engaged and have a future in it. Whereas, you and I, we may have our days numbered, I guess. But getting back to timekeeping, and I thought about this book. I interviewed Zach Weinersmith last week about his book, A City on Mars. I actually spoke to Elon Musk on Twitter, X Spaces rather, a couple of weeks ago. And I asked him, look, man, you can't be serious about going to Mars. It's basically a one-way death trip if you make it. The best case is that you die on the way, and you may like it, but the people traveling with you, when they're as rich as you on the spaceship, it doesn't matter that you had 250 billion US dollars, who cares when you're, in the middle of, the halfway point to get to Mars, and you still have 6 months left with this guy. So I said, are you really serious about this? I mean, he has 10, 11, 12 kids. We don't know for sure. But what are you doing here, buddy? And he really couldn't answer. And his mom broke in and said, well, we don't have to worry about that for a while. And but made me think about interplanetary timekeeping. Let's say we do get there. Mars could be as close as, I think, 4 light minutes from Earth. It could be as far as 20. Imagine civilizations set up there. It's impossible for any real-time guidance activities, but what would be sort of a standard? Let's make the standard now, instead of the piecemeal network of, that was set by railroad architects that you depict in the book, and the other ways of keeping time. What would be, if you were Musk or you were on his board, how would you partition the timing and coordination of time?
So we have, in a very deep way, gone to a sort of universal standard for time, right? We currently don't define time anymore in terms of the rotation of the Earth. I mean, colloquially we do, but the official SI definition of time is that the second is 9,192,631,770 oscillations of the light emitted as cesium atoms move between two particular hyperfine states. And that is a fixed definition that we use for, to define what is 1 second. And then you can just use seconds as the basis for whatever, completely decoupled from the rotation of the Earth. There's a really good series of science fiction novels by Vernor Vinge. The one that I'm thinking of in particular is A Deepness in the Sky, which has civilization as their interstellar travelers. And then they talk about everything in terms of kiloseconds and megaseconds and, so multiples of so many thousand seconds. And that works actually, surprisingly well. So if you're going to start organizing things on an interplanetary scale, probably you would go for completely decoupling from any of the planets and just say, look, a second is a second is a second. You got a cesium atom, you measure its hyperfine splitting, you know what a second is. Now just count those, right? And that's the way to go, probably. Make it not tied to hours as we currently know them, but some multiple of seconds as we currently know them.
Hey, back one last time to ask you for something special, which will give you something special. If you'd like a real piece of space schmutz, real live meteorite, or if you'd just like to find out about the insights that we can glean from Nobel laureates, billionaires, astronauts, and acclaimed authors in space, science, and technology, you can with my free Monday Magic newsletter. Please go to briankeating.com/list and sign up now. As a token of my gratitude, I give away a real live piece of space dust, a 4 billion year old meteorite, to one lucky subscriber each month. I also provide them guaranteed if you have a .edu email address and you live in the United States. Go to briankeating.com/edu for that special offer. Now back to the remaining moments of this wonderful episode about time.
Yeah, you mentioned Vernor Vinge. I can't resist mentioning he's a proud alum of UCSD in math department. We have a surprising number of great, illustrious science fiction authors, from David Brin, past guest on the podcast, Greg Benford, also a guest on the podcast, Kim Stanley Robinson, past guest, and non-graduate, but he went on to some success, a guy by the name of Andy Weir. They all did time here at UC San Diego.
Yeah, he did. He's done well for himself.
Yeah, I mean, can you imagine what kind of career he had if he actually had a BA from UCSD? Can you imagine what he could have gone on to?
Yeah.
God, we could use that Weir wing of the astronomy.
Yeah, exactly.
So, let's talk about your training, your research, before we get back to some timekeeping, which is intimately related. As I mentioned, we had Bill Phillips on last year. The sense that I got is this is great, and it's wonderful technology, atomic fountains, and going way beyond the cesium. But I mean, as you say in the book, light travels 1 foot per nanosecond. So you're talking about billions of nanoseconds, billions of feet. I mean, we can't even conceive of using there are other systematic effects that come into play, that, the Earth's magnetic field and others that will have bigger effects if you try to use it as a clock. So what's the point of it other than gathering and garnering Nobel Prize? Is there a technological implication? Not that all science must have technology downstream from it, but taking your thesis work on forward, what types of technology could result from, having attosecond clocks, for example?
There are these experiments that have been done in a couple of places at NIST in Boulder, and then there's a group in Tokyo more recently. They're doing these experimental clocks. And you can start to do exotic physics things with them. So one of my favorite demonstration experiments ever is this experiment with aluminum ion clocks at NIST in Boulder, where they made 2 identical clocks using a transition in aluminum ions as the basis of their measurement of frequency. And then they raised one of them about 1 foot above the other. They just used hydraulic jacks to lift the whole laser table up a foot higher. And they could see that these tick at distinctly different rates, right? And this is the effect of gravity on time. And you can start to exploit that to do very sensitive tests of general relativity. Or you can use it for geodesy, for looking at the gravitational profile of the Earth, basically, move to different places and compare these ultra precise atomic clocks. If you want to get really, pardon the expression, pie in the sky, you can put these things on satellites and make a detector for gravitational waves. So if you had a network of satellites with ultra precise atomic clocks in them, we know from LIGO, as gravitational wave comes in, the space expands and contracts a little bit, and you see the mirrors in your interferometer move. You could also, with a network of atomic clocks, space and time are different aspects of the same thing in relativity. Time would speed up and slow down slightly, and you could see that as sort of a rippling through your network of ultra-precise clocks. And that would give you an ability to measure gravitational waves in a regime of sort of wavelengths and frequency of those waves that you can't access readily other ways, which would be really interesting. And then there's even more like wild stuff that we aren't sure exists, like possibility that the constants of nature change over time. So all of these atomic clocks are based on the energy splitting between two levels in an atom, and those are set by things like the ratio of the electric charge on an electron to Planck's constant and the speed of light. And the different transitions in different atoms depend differently on that ratio. So some will get bigger if this collection of constants called the fine structure constant, if that gets bigger, some of these transitions will move to higher frequencies, and others will move to lower frequencies. So if you compare two atomic clocks using different kinds of atoms, and you look over time, if your clocks are precise enough, you can tell, is the fine structure constant getting bigger or smaller over time? And there are some really exotic theories in the sort of string theory and other extensions beyond the standard model that predict that is a thing that could happen, that the ratio of the electric charge and the speed of light and Planck's constant would be getting bigger or smaller over time. And you could test that directly with sufficiently precise atomic clocks, just comparing their frequencies over the course of a year, 5 years, 10 years. You can do that at a level where you really test some of these theories.
So when we look going backwards in time, starting with Einstein and the relativity of simultaneity and the Newtonian clockwork universe, and then going back even further back to these ancient sorts of calendars that you talk about, along with their concomitant predictions of doom. What is it about time, especially that kind of harkens, terrifies, maybe instills fear in mankind, that so much so that when we have these paradigmatic shifts like Newtonian or and even changing calendars, that you have these kind of almost existential effects on humanity? Can you speculate? You're a physicist, not a psychologist, but nevertheless, what is it about time and not space? I mean, space is equally mysterious and may have aspects of quantization and philosophical ramifications, but why is it time in particular, since the time of the Mayans and even before, I'm sure, that has so imprinted on the psychology of man that we can't seem to escape it?
Yeah, I think it's, ultimately it comes down to, the thing I said at the beginning, that we experience time in one direction only, right? We move inexorably from the past to the present to the future, or, we're sort of eternally in the present, but we only see time moving in one direction, right? Space, I can go outside, I can walk east, I can walk west, I can walk north and south, I can jump not all that high anymore, but I can get up in the air a little bit, or climb upstairs, go downstairs, right? I can move all sorts of different directions in space. Time, you really only, it's a one-way trip, right? None of us are getting any younger. We're moving forward into the future at 1 second per second. At the same time, there's sort of this tension that time necessarily involves these cycles, right? We measure time by counting the repeated ticks of something that's doing the same thing over and over. We mark the passage of days and years through these cycles. And so there's this tension between sort of the cyclical nature of things, right? Everything comes around again. It's winter now, soon it'll be spring, then it'll be summer, and eventually it'll be winter again, and we repeat that cycle of seasons over and over. Not so much in California, but we have this cyclical thing that's going on, but at the same time we move forward into the future in an irreversible kind of way. And that tension, I think, really brings in a certain amount of fascination. So you have these sort of competing, and there's threads in all different cultures, a sort of competition between, the very Christian sort of worldview where, the world has a beginning and it moves forward to, the book of Revelations, and then it comes to an end. And it's a linear progression from point A to, from point alpha to point omega, and then we're done, versus sort of a more cyclical kind of thing like you see in some of the Eastern cultures where you have ideas of rebirth and repetition. The Mayan calendar was really all about these cycles that repeat over and over and over and go, come back around many times again. And there's that tension between those two things that drives a lot of science and philosophy and culture, and just thinking about how do those two things coexist? How does that linear march into the future and this cyclical repetition, how do those play with each other?
Looking at back towards the career that you've had and working with someone like Bill Phillips. I read a quote that you paraphrased from him on Twitter. Everyone should follow Chad on Twitter as well. You said, in his name, most people are very happy to be reminded of things that they already know. You rarely lose by including too much background information. How do you apply that kind of advice? That's for seminars, but when you're teaching something fundamentally new, of course it's something they don't know, so how do you remind them of something when it's ab initio? It's completely new for them, as in your wonderful book.
Yeah, it's a tricky balance, right? I'm teaching this term. I'm teaching Newtonian mechanics for first year college students. That's really a mix of that sort of thing, because we rely a lot on, look, we're talking about the physics of the motion of everyday objects. How these things work, right? If I take a ball and I throw it to, in your general direction, you can make a pretty good prediction of where that ball is going to be. And, most students can at least make a good effort at catching the ball, right? We know how things tend to move. But at the same time, we don't know the physics. We don't know how to quantitatively predict some of these things, and so there's a going back and forth between, okay, you have an intuition for how this works, and also now I'm going to do something that is unexpected, that follows from the principles of physics that lead to the thing that you did understand, and then sort of trying to show people that no, these are consistent, right? One of my favorite demos that's dumb, you can do it at your own house, is you get like a basketball or a soccer ball, a heavy ball that'll bounce, and a light one like a racquetball or a tennis ball, and you hold the light ball right on top of the heavy one and drop it. If you drop either one from sort of chest height, it'll bounce back maybe to your waist. But if you drop one on top of the light one on top of the heavy one, when it hits the ground, it'll kick way up into the air and bounce off the ceiling. And you can explain that really easily using the physics of momentum, and just understanding the principles that are involved in collisions. Very unexpected, always gets a good reaction from a class, or do it with elementary school kids. They love that, and then they're always do the heavy one, see if you can put it through the ceiling. But but understanding that idea, gets you some new understanding of principles of physics that you can go on and apply to unfamiliar things.
And I should point out, speaking of time and branding, I think that Patek Philippe should rebrand. At least one watch should be a Patek Philippe's, and they should partner with Bill. Maybe they could get him a free watch. He needs it, I'm sure.
He's doing okay.
So let's finish up by talking about education. You're renowned not only for your books. You're one of the few people that I know who hasn't. I don't think you've been on Jeopardy, but you've been a Jeopardy question or a Jeopardy answer.
I have a short video clip in which Alex Trebek says my name, which that's bucket list stuff.
What, in terms of how you divide your time between teaching, keeping research in mind, writing popular books, and also, technical mentorship. How do you divide your time, and what is what is kind of your philosophy overall, and how you keep balance between these different aspects of your life?
It changes year to year and term to term, and in the course of the academic year. It depends a lot on what I'm teaching at any given time. This term, January through now, has been really heavy teaching just because of the nature of the particular course I'm doing. But, I try to make a point to block out a few hours a day in the morning. To my chagrin, I've turned into a morning person in my middle age. And so I get up really early because, I get up at like 5 and I walk the dog and feed the dog and then, get the kids up and off to school, and then I'm in the office at like 7:30. So I block out some time in the morning for working on my own stuff, for working on books and blog posts and articles and that kind of thing. And that's really important to sort of separate out that particular time. And then the teaching is, that's on a relatively rigid schedule. And, in the summer, it's more focused on research. I frequently have students working in my lab on various projects. And, that's more of a, meet with them daily and, okay, what are you doing? Okay, try this thing next and, or do this and talk about what the future of the project is. And so that's its own process. So, these things go in cycles. The academic year is September to June, and we're in session, out of session, and things move around a little bit. But
yeah, that's the most important calendar that you don't mention in the book. You mentioned Gregorian, Mayan, but you don't mention the academic
calendar. Yeah, the starts in September. Everybody freaks out at the end of the term, and and then there's a sort of a period in May where everybody's mad because it's coming to the end of the year and everybody's nerves are shot, and then you got 2 weeks to graduation and everybody's snippy at each other, and then and then there's a big sigh of relief, and then we're into the summer.
So when you were writing, I don't think you're still as active writing for Forbes as you were once several years ago. But you published a wonderful little article, which basically becomes part of the book. But you talk about the 5 biggest surprises. So maybe you can end with, of all the biggest surprises in the history of timekeeping, the characters, the tools, the kind of existential dread that came about in many ways. Tell me, Chad, what was sort of the greatest, surprise to you writing this book? It's always kind of a form of me-search when you do this type of research, right? So what was your favorite surprise as we wrap up?
The thing that I was most surprised to learn, and the book started as a course that I offered a couple of times at Union with the same title, Brief History of Timekeeping, which I was stunned that nobody had used. The most surprising thing was learning that mechanical clocks and sandglasses are of comparable vintage. Right, you think of a sandglass, an hourglass, with the sands in an hourglass are the days of our lives kind of thing. You think that would be like a technology that's just 10,000 years old. People have been doing this forever, but it's actually the first verified reference to that is in the early 1300s. There's a mural on a wall in a church in Siena, Italy, that shows an hourglass in recognizable form, and that's the first time that one of those is unambiguously depicted. And at around the same time, you have mechanical clocks. People had invented those two technologies at about the same time. And the other interesting thing about them is that nobody knows who invented either. They just sort of show up, right? There are just hourglasses are a thing in Europe. People have them. They're using them to measure time, and it's just kind of everywhere. And mechanical clocks just start showing up in churches in that 1300 kind of range. They just start appearing, and there's no one inventor that we can point at and say this guy is the one who came up with the idea of the mechanical clock. It's just suddenly they're everywhere. So it's a really interesting testament to sort of the power of anonymous tinkerers, right? Somebody somebody figured out how to make this work, and it succeeded so well that nobody remembers who they are anymore.
Chad Orzel, professor, Union College in good old Schenectady, New York, my former homeland of New York, at least, although I was more in the deep south of New York. I want to thank you for your time in this wonderful book and sending me a copy, and I've got my own audio copy, which I devoured as well. Chad, thank you so much for spending so much of your time, your valuable time. I just want to say one last thing. If it's true that you believe that it's true that a man who has one clock knows what time it is, but a man with two clocks never is sure, that must
always
make you
confused.
must make you one of the most confused people in the world. But this book is incredibly easy to read, clear, and just a delight to read and listen to. Chad, thank you so much for spending your time today.
Yeah, thank you for having me on. This was fun.
If you watch all the way to the end, I know you'll love this interview with Nobel Prize winner Bill Phillips, who's Chad Orzel's PhD advisor. And click here for a playlist of the best episodes from the past few weeks. See you next time on Into the Impossible.